Hi, I'm Mr. Troha, and today we're going to be talking about the formation of the solar system. So there are a couple of different hypotheses about how the solar system was created. One of these is the encounter hypothesis. This is where there was already a star, our sun, and another star came by, and the tidal forces ended up pulling different parts of the gases of the stars, and those then formed the planets. Of course, this type of event actually doesn't predict very many planets, and we end up having quite a few. So, moving to our more accepted theory, this is the nebular hypothesis. And this is the generally the most accepted hypothesis of the formation of the solar system. This is one where there is a star that dies and goes into a supernova, spewing gas and dust and particles all over the place, and also creating a spinning effect. So the dust and gas start spiraling around in one direction. So during that spiraling, the gas and the dust start to gather into the middle. As that gas and dust gathers into the middle, it starts to heat up, it starts to gain mass. Instead of being a big sphere, it now flattens into more of a disc shape with a bulge in the middle. And so this takes a very long time. After about 10 billion years, the sun started to form. And we started to have some different reactions in between those gases. They're now the sun. So this would have been about 4.5 billion years ago. So all the other dust and gas that was in the disk outside of the center starts to gather together as well. This is called accretion. Accretion is when these particles stick together to form larger pieces. So these particles collide, they stick together, they're continuing to circulate around, but as they stick together, they get larger. Could be a few kilometers across. These are now called planetesimals. So these planetesimals are moving around a circle orbiting that center mass that will become our sun. As they get larger, they get more gravity, which ends up pulling in more gas and dust. And eventually these planetesimals form together into larger groups that are called protoplanets. And in our case, we have 8 of these protoplanets then became planets, which we know today. So that was takes 10 to 25 million years for all this to happen. Now, how do we know this is the case? Of course, in science, we need evidence for things. So there's a couple of different things that I want to point to you. This is an image of Beta Pictoris, and it is a pretty close by star. It's only 63 light years away, and it's about 20 million years old. So it's in this process. So we're seeing these disks of gas and dust, and we have that center part there, and then the gas and dust out here on the sides. Here's a nebula. We talk about the nebular hypothesis. Well, this is the Orion Nebula. So this is there was a star that it was destroyed, created all this gas and dust, and if you look at these images, we see if you notice down here in the bottom right, there's an image zoomed in to some of these things in the Orion Nebula. There are about 150 of these protoplanetary disks, and so this we have this little star here, and we have some disk around it that are currently in that accretion phase. Now, looking at our solar system, the way it's set up, we notice that we have the sun in the center. Here we have the sun in the center, and then we have the planets, and the planets are slightly elliptical. Their orbits are slightly elliptical. This was actually something found by Johannes Kepler with his data from Tycho Brahe. They he ended up forming Kepler's laws, and one of those things that he found out was that the orbits are slightly elliptical, but they're very close to circular. The planetary orbits are all essentially on the same plane, meaning notice that they're one flat disk there, with the exception of this white one going around, but notice that that's a comet. It's not a planet. And they all are traveling in the same direction, which is counterclockwise if you're looking from the top. So everything's rotating. So again, the idea of this evidence that all the gas and dust was rotating in a singular direction and eventually accumulated in space. One of Newton's laws is that the law of inertia, saying that once things start moving, they're going to continue to move in that direction unless there's a force stopping it. And in space, there isn't friction from air or anything like that, so it just keeps traveling in that same direction. So here's another piece of evidence. The planets rotate in the same direction. And again, looking from the top, they'd be going counterclockwise. Now you notice there are two, if you look closely. This is Venus. We have Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Venus is actually rotating the opposite direction, and so is, Uranus is also doing that. And so, but it's on its side, and so there's ideas, the theories are that Uranus was hit a number of times, one or more times, that caused it to rotate so that it looks like it's rotating the other direction. And Venus also, their thought was that it's actually started out rotating the same as all the other ones, but now it is flipped. Its axis is actually flipped, so even though the material is rotating the same way it started, because it's flipped, it looks like it's rotating the opposite direction. That's one idea. There's another idea that possibly it was struck by a large object and caused that to happen, but either way, those are the two that are different, but they have hypotheses that they originally were going in the same direction as all the other ones. The solar system is highly differentiated. Now, what does differentiated mean? It means that we have heavier things towards the center, we have the lighter things, and when I say heavier and lighter, we're actually looking at density right here. In the center, where you have the most gravity, the most mass, which is the sun, it has pulled the more dense material towards it. And so the more dense material was towards the center, and so then as the accretion happened, we have denser, rockier planets. Those are the 4 terrestrial planets that are closer to the sun. And then as you got farther away, that was the lighter gas, the lighter material, and we have a lower density. Those. The asteroid belt, this is just, we're kind of away from the evidence piece, but this is an interesting thing. Asteroid belt is in between Mars and Jupiter, and it could have been that 9th planet. Ideally, all those asteroids would have accumulated together and maybe formed a planet in between Mars and Jupiter. But Jupiter is so large and has so much mass that as it was rotating it around, it really kept that object from gathering together. And so now we have a bunch of asteroids. Now, this picture is kind of misleading. It looks like they're all close together. They're actually very, very far apart, and we'll talk about this more in the next week. So, what does it actually mean to be a planet? We talk about these planets. There are 3 requirements that are set out by the International Astronomical Union, and which is kind of the governing body here. So must satisfy these 3 requirements. It must orbit the sun. Well, there's lots of things that orbit the sun, so we could have a lot of planets if that was the only thing. It must be roughly spherical. So that's this idea that as it accumulated, it had enough of its own gravity to form into a sphere. And it must have cleared its orbits of other planetesimals, which means that in the orbit of the object, it can't be running into other objects out in space, other planetesimals. And Pluto was a planet, and it now is not a planet anymore. It's considered a dwarf planet, and that's the one thing that was its downfall, as we say here, is that it goes through the Kuiper Belt, which is an area that has a lot of other large objects and planetesimals. So here we are. Here's a picture of our solar system. We have the sun in the center. We have Mercury, Venus, Earth, Mars. Those are all within 1.5 atomic astronomical units. Remember, an astronomical unit is about 150 million kilometers, and it's the distance from the Earth to the sun. Then we have our asteroid belt. Then we have Jupiter, which is 5 astronomical units. Jupiter, Saturn, Uranus, Neptune. Okay, they're all in that plane. They're all considered the planets. So 4 inner terrestrial planets. The asteroid belt, 4 outer gas planets. Again, they're mostly gas. And then we have the Kuiper belt, which is think of it like that asteroid belt, but it's kind of larger objects. It's much farther out. Takes up a large area, and Pluto goes through that area. And then we have the Oort cloud, which is really the outer edge of our solar system. Here you can see those things. This is a logarithmic scale, which basically means that the same distance is 1 factor of 10. So it's just a way of kind of scrunching everything. So different scales. So we have Voyager 1, Voyager 2. Those are some spacecraft that were sent out by NASA. Voyager 2 passed Neptune around 1989. And so we have here is this area that the solar winds push out and the rest of the universe pushes in. That's where that area collides. And then out here into the outer reaches of our solar system is the Oort cloud. So, okay, well, thank you very much for listening about the formation of the solar system, and we'll see you next time.